Please use the chat function when you wish to ask any questions, or you can raise your hand and we can discuss things verbally. So either's okay, but if you want to drop any comments into the chat function, we'll do the very, very best to answer them. I'll raise them in open forum in the breakout sessions. So we have a pretty exciting agenda today, and you should have seen the agenda. We have my introduction, followed by a keynote talk from Jenni McDonnell MBE on industrial energy efficiency. Mark Allen will give us an overview of crushing and milling and grinding state of the art. Professor Lenny Cole will tell us all about techno-economic analysis and lifecycle assessment and how they may be used in sustainable manufacturing, particularly in this case towards energy efficient manufacturing. Then we have Professor Sam Johara, who's going to tell us about heat exchange systems. So all of these talks, or 3 of these talks, will be followed by breakouts. So onto the introduction. This is becoming less important as we move forward with our network, but I'm the lead, the principal investigator of the Transforming Foundation Industries Network Plus. My deputy is Susan Bernal Lopez. I'm from the University of Sheffield. Susan Bernal Lopez is my deputy from the University of Leeds. The other people on the management committee are William Sampson from Manchester, Cameron Pladel Pierce from the University of Swansea. Our industrial chair is Chris McDonald, and you've been contacted on a regular basis from Debbie, who is the marketing officer for the Network Plus, and also from Neil, who's the network manager. Next slide, please. So what are the themes within the Network Plus? I think probably, the audience could more or less guess the types of themes that we're likely to address. Energy efficiency is today. Resource efficiency will be the topic on circular economy, will be the topic of upcoming workshops and indeed calls for mini projects. Next generation processes, new things coming down the line, which we address through our Blue Skies Green Future webinar series, manufacturing informatics, digitalization, and we must also address policy and advocacy, equality and diversity and inclusion. These are important aspects within the foundation industries. Next slide, please. Just shows you know where we are and in the kind of flow of our network. Our official start was January 2021. On the 1st, it was a hard start, and we got ourselves going as quickly as possible. Our launch was in Feb, so we had a launch event, which was an overview of the things we're likely to do within the network. We've already had one workshop on road mapping, which many of you may well have attended. We've just completed our first call in energy efficient manufacturing. We're in the reviewing stage of those calls, and anybody who's bid for any monies in that call for funding will get an answer pretty soon as to whether they have been successful or not. Today is our energy efficient processes workshop, so thank you for attending. And as we move forward, we have more events coming up. Our next project call is going to be resource recovery and industrial symbiosis, and there will be a workshop linked to that. We'll keep you all up to date through our outlets. Debbie will look after the advertising of events to make sure that you know all about what's coming up. And I hope you can attend future events as well as this one. We have, in addition to what you can see in front of you, our Blue Skies Green Future webinar series, which showcases groundbreaking technologies for the foundation industries. We've had 3 of those already. We'll restart that series in September, where towards the end of go through to the end of the year, where we have 4 headline speakers telling you all about exciting new potential things, which are not necessarily around the corner commercialized, but could be the future in the foundation industries. Oh, sorry, can you go ahead and forward me another one? So this is the agenda. I've been through this already, but you can see it in front of you. We have Jenni McDonnell MBE, Mark Allen, Professor Kaur, and Professor Juhara, all speaking on energy-related topics. Next one, please. Okay, so how can we help? Well, the TFI Network Plus is here to link academics with industrialists, in part to create projects, in part to have discussions, but the whole concept of what we're trying to do is to get conversations going and help seed concepts and ideas through our mini project fund. So please join our network. Please come to the meetings in the future. I think they're very important for the foundation industries in our view, and I hope you also feel that is the case. Next slide, please. So thank you. We have a dedicated email address, tfinetworkplus@sheffield.ac.uk, and you can see here clearly the web address that you can join and become a member at, and I hope that today, if you haven't already done so, inspires you to become a member. Okay, so I think we can move on to the main topics now of the workshop today. And our first speaker is Jenni McDonnell my apologies. Jenni McDonnell MBE is from the KTN, and she's going to talk to you about industrial energy efficiency, reducing the energy demand for manufacturing processes. So I'm going to hand over to you, Jenni, to give us your presentation.
Thank you very much, Ian. And hello, everyone. As Ian said, my name is Jenni McDonnell and I work at KTN. I'm the technical lead for thermal energy at KTN, and I've been working with the government for several years on their industrial decarbonisation programmes. In particular, at the moment, I'm working with BEIS on the Industrial Energy Transformation Fund, and I'll talk to you about that shortly. So if you can move on to the next slide, please. So before I get into describing the fund, I thought it'd be a good idea to just talk about some of the barriers to manufacturers deploying industrial energy efficiency and look at some of the technologies that they are actually having to go at. So in terms of the barriers, I would think these three are probably common to every manufacturing sector in the UK. As a challenge that needs to be overcome to allow them to start reducing their energy demand and carbon emissions. So the first one is the fact that they are competing in an international market. So investing in technologies that might not increase production volumes and in some cases might even impact on production is always going to be a challenge to sell to their bosses. Obviously, energy efficiency is reducing the energy demand, and that's going to bring down the unit cost of production. But if it does anything to affect the production volume, that's their core business, that is a challenge. And kind of linked to that as well is the return on investment. So the UK sites, I know, are keen to do more to reduce their carbon emissions and their energy demand. But again, because they're operating in an international market, that cost of production is so important and needs to stay competitive. So their return on investment has to be about 2 years for it to be something that they would consider. And that can then make more long-term investments and R&D projects are much harder to sell to their headquarters. And in a lot of cases in the UK, the manufacturers are owned by overseas companies who may not be as keen on carbon reduction as the UK. The second barrier, I would say, is the lack of knowledge. By no means does this relate to every manufacturing site in the UK, but we have seen over the last few years a number of manufacturers coming to us for help to know what technologies are out there and what they can do to reduce their energy demand. And not every manufacturing site has an energy manager that understands the energy sector and the technologies. They are manufacturers, and energy is just something that they need to be able to produce the products. So understanding what energy efficiency technologies exist, and particularly in relation to the manufacturing process itself. They will have done the quick wins like changing the LED lighting and things like that, but the main energy demand and the main carbon emissions are coming from that manufacturing process, usually related to the heat and cooling that they need to make the product. And we found that peer learning is the most effective way to reassure manufacturers as well, to give them confidence that the technologies would work on their site as well. And it doesn't necessarily have to be seen on a site from one of their competitors in their manufacturing sector. It can be another type of manufacturing, but if they can see that it's working there, they're more likely to give it a go. And we're trying to help them to understand what is out there that they could try. I think the third barrier, unfortunately, is the public funding timescales. So a lot of manufacturers will need support from public funding to de-risk these projects. But because of the way public funding works and funds are allocated by the Treasury, those timescales to deliver those projects they're quite short, sort of 3 to 4 years. So we have been trying to encourage manufacturers to be ready to move when these funding opportunities come along, to make the most of those funds and to allow them to get to that sort of net zero goal that they have now. So moving on to the next slide. Now, as I say, that I do think from that gloom and doom, there is a light at the end of the tunnel. Over the last 18 months to 2 years particularly, I've heard a lot more manufacturers discussing their new net zero strategy and having a goal to get to net zero by 2035, 2040. And that is very encouraging. It does mean that they're now actively looking for solutions to help them become more energy efficient. And from the work that I've done with the government, I think these are probably the top 5 energy efficiency improvements that I have seen happening at manufacturing sites in the UK. The first one, without a doubt, the most popular solution is heat recovery. Heat recovery on its own, or heat recovery with organic Rankine cycle or other ways of converting that heat into power that can be then reused in the manufacturing process. That is happening everywhere. The second one I would say is improved process controls and automation. A lot of manufacturers will have a little bit of process control. Maybe the furnace has process controls, but not all the way along the manufacturing line. And that is something that they're now starting to look at. How can we join the whole manufacturing process together as a system and build in AI and automation to make the process more energy efficient? And then the last 3 on that list are all kind of related. This is process equipment and what can we change to sort of deploy and install more energy efficient versions of process equipment. So a lot of manufacturers looking at new furnaces, boilers, chillers, compressors, things that they've had for 20 years. They don't want to just do a like for like replacement. They're looking for something that is going to make the process a lot more energy efficient and sort of future-proof their production line. Variable speed drives as well, another popular one. So improving the performance of motors that they have all the way along the manufacturing line, and also energy efficient heat exchangers. And I've put a few pictures there, some examples of Electrotherm do a great heat recovery and ORC unit, and also heat exchangers in food manufacturing is quite popular. Next slide. So now to talk about one of the funding opportunities. Obviously, this is a TFI network, and I'm sure we will talk about the TFI competitions, which is R&D support for industrial energy efficiency. The Industrial Energy Transformation Fund is also supporting businesses with high energy use to cut their energy demand and reduce their carbon emissions. But this fund isn't R&D, it's capital investment for energy efficiency and decarbonisation. So it's allowing manufacturing sites in England, Wales and Northern Ireland to apply for the funding and do something, install something that's going to make a difference straight away and allow them to achieve energy savings straight away. There are the whole fund is 289 million. We had the first round of funding last year with 30 million spent, and we're currently in the spring window that's open right now, worth 40 million. Phase 2 will start in the autumn, and that's the remaining 219 million, and that will last up to 2024. So there are 2 competitions open at the moment. As I say, in the spring window, you can either bid to do a feasibility or engineering study, preparing for future deployment projects, and that can either be in energy efficiency or decarbonisation, or you can bid into the deployment competition, which is deploying mature energy efficiency technologies. So that's technologies that are around TRL 8 to 9. Both those competitions are open at the moment. It does close on the 14th of July, so we've only got about 3 weeks left for this round of funding, but as I say, it'll be back in the autumn. Next slide. So just to look at the 2 competitions in a little bit more detail, as I said, the feasibility and engineering studies is building that pipeline of future deployment projects around energy efficiency or decarbonisation. What it won't do, unfortunately, is fund sites to do energy modelling and understand their energy demand across their site, or do any kind of market analysis and review lots of different technologies before they choose what it is they want to deploy. You have to have done that piece of work already when you come to the IETF, and the feasibility study is then allowing you to check the technical and economic viability of deploying a particular technology on your site. So these projects can be collaborative or single applicant, and it has to be led by the business that operates the manufacturing site. So if it's single applicant, it's the manufacturer, but they can have subcontractors and work with technology providers in that way. The sites, so the studies have to be based on a site in England, Wales and Northern Ireland. If you have sites in Scotland, there is a Scottish government version of the IETF. The scope's almost identical, and their next round of funding opens in the autumn as well. And the lead applicant for this one has to be the end beneficiary of whatever you're doing. So for instance, if you're doing a study to look at heat recovery, that energy saved has to be reused on the manufacturing process. You can't be given away to a local community or nearby business. But the good news is the manufacturer can partner with other businesses, research and technology organisations, academics and public sector organisations. As long as they have an active role in the project, then they can be a partner. Your total study costs have to be, that's your grant plus match funding, has to be at least £50,000 for engineering studies and at least £30,000 for feasibility. Next slide. And then the deployment competition, as I say, if you're ready to do something straight away, this is the one for you. You can deploy mature energy efficiency technologies that improve the efficiency of the manufacturing process itself. And this can be, again, collaborative or single applicant, must be led by the business that owns the manufacturing site where the technology is going to be deployed, and has to be the end beneficiary. And as this isn't an R&D project, at the end of the project, the technology has to be fully installed and operating or ready to switch on. So you get those energy savings straight away as soon as the project is over. For this competition, the grant alone must be at least £100,000, and then your match funding goes on top of that. Next slide. So I just wanted to share 3 case studies. These were projects that were funded in the first round of the competition last summer. First of all, we have Hinton Perry and Davenhill. They're a ceramics company. They make the Dreadnought tiles and bricks. And they are currently looking at whether they can improve the energy efficiency of their brick and tile dryers by capturing the waste heat from their kiln flue gas, using hot oil to transfer that heat to the dryer, and then recirculating that heat to actually dry the tiles and bricks, instead of using gas and electricity, which is how they do it now. The company has almost finished the study, and they reckon they're going to save about 900 tonnes of CO2 emissions, so about 10% of their current CO2 emissions by doing this. So that's going really well. I think they will continue to deployment. Next slide. The next one is Tate and Lyle Sugars. They have a sugar refinery based in London. They're also doing a study and working with engineering consultants, Fitchner, and also a technology provider called PMW Technology, and they have developed a cryogenic carbon capture process called A3C. And so PMW, this study is looking at the feasibility of deploying this carbon capture technology at the refinery to capture the CO2 from the flue gas as a frost, and then using that recovered carbon dioxide as a revenue stream for Tate and Lyle. Next slide. And finally, one of the deployment projects, SR Oil is a refinery up in the northwest, and they are deploying a brand new furnace for their process. They currently have oil-fired furnace, and they are deploying a hydrogen-ready furnace. So it won't be burning on hydrogen straight away, but the furnace that's going in will be capable of having 100% hydrogen to run it. It's also looking at other energy efficiency improvements such as heat recovery, and they hope to be the first oil refinery in the UK to run on 100% hydrogen. And I think that's it. Yeah. So some great examples of what you can do around industrial energy efficiency.
Thank you very much, Jenny. That was a fantastic overview of the funding landscape. And we can open up your talk to further questions. I certainly have one, Jenny. Your funding is quite broad.
Yes.
And not specific to the foundation industries.
No.
Have you any idea of the percentage in your first call that went to the foundation industries?
Not off the top of my head. It was a real mixture, though.
Okay.
You know, there wasn't one sector that dominated, and we had a good mix, and a good mix of sites across England, Wales, and Northern Ireland as well. So we were pleased with that.
Could you expand a little bit on the, you had some feasibility aspects to it and involvement of academics, perhaps. Could you expand on that a little bit to explain how that relationship might work in the context of some of these grants?
Well, for the, probably more for the decarbonisation theme. For decarbonisation, because we know some of those technologies aren't near to market yet, the TRL level for that is TRL 7. The IETF won't fund demonstration or testing of a solution, but it will allow, I guess, academics to work with manufacturers to just explore whether something would work on their site, and then look elsewhere for funding to be able to demonstrate it. So I would think that's probably the best way to get involved.
Okay. You had your hand raised, Mark, I noticed.
Yeah, I just wanted to ask Jenny whether there were any examples of projects where they were looking at capturing of low-grade heat, because that's one of the work streams in the TFI network, TFI hub.
Yeah, I don't think so. So the IETF, the way people are assessed for the deployment is the grant versus the energy savings. So that value for money is the score is what kind of drives who wins. So they're really looking for projects that are saving a lot of energy, and that might make that a challenge.
Okay.
Are there any further questions for Jenny before we move on to the next talk? Oh, sorry. Is there any, this is from Sudip Bose, is there any success story of improving energy efficiency through scavenging waste heat using thermoelectric generators?
Not funded, but I have had, I'm talking to a lot of companies that are obviously preparing applications at the moment, and that is something that I have spoken to someone about. So we'll keep fingers crossed and see if they get through. Yeah,
it's an interesting technology for, if people don't know what thermoelectrics do, they may do, but they generate electricity from waste heat in general. That's the operating kind of mode that you might anticipate in the energy intensive industries.
Mm-hmm.
So thank you for that question.
The nice thing about IETF is it's technology neutral. So as long as what you're doing is reducing the energy demand, and you can get a good value for money score, then BEIs are open to ideas. But it is, as I say, it's a capital investment fund rather than R&D.
Okay. So any further questions? I'm trying to pick the ones up in the chat. Okay, so thank you very much, and congratulations again for your
Thank you very much.
recent award of an MBE, a fantastic achievement. So now we have Mark Allen from ENGCO, who's currently in Singapore. So we're going to thank him very much for spending his evening, I believe. Is that correct?
Almost. It's only 5:30, so it's not too bad.
It's not so bad. Okay, so you're kind of ish in the working hours. Yeah. And his expertise is in comminution. I can never say that. So I'm going to say reduction in length scales in order to within industrial processes. In most industries, that's crushing, milling, grinding. And he's going to has a wonderful title: Improving the Daily Grind, Getting the Most Out of Your Energy from Crushing and Milling. So I'll hand over to you, Mark.
Thanks very much, Ian. Thanks for that introduction. I'll just put my slides up on screen, if that's okay. So just bear with me a second. Okay, so yeah, as Ian said, I'm currently in Singapore, and I've been here for about the last 5 years. You might be able to tell from my accent, though, I am not Singaporean, I'm Australian. Have had a long history in working in climate change, decarbonisation and energy management. And because a lot of that's in Australia, a lot of it comes from the mining and mineral processing industry, which is a very important part of the Australian economy. Very good at digging things up and sending them places, which involves a lot of comminution, which is how one pronounces the word. But I often refer to it as turning big rocks into little rocks, which is really what it is at its heart. So just, starting off with a bit of a quote from the International Energy Agency, and people have probably heard something very similar to this before, but it's that energy efficiency is the first fuel. So it's the first place that we should go to with regard to, optimizing our energy consumption across the plant, and provides a great way to actually reduce emissions and reduce costs. So I'm going to look at 3 areas today in this fairly short presentation. So we'll start off with some information around the context. Why do we even care about energy efficiency in crushing and grinding, or even energy efficiency as a whole? So, this is taking a pretty broad view on decarbonisation and how that will play out. We'll look at the size of the prize. So I just finished a piece of work on quantifying how much energy crushing and grinding uses globally for the mining industry. And there's a bit of an extension to that to, quarrying and cement and other things like that. But, highlighting how much energy in total does it take to turn big rocks into little rocks. And then looking at some of the opportunities, some of the things that we can do to try and reduce that energy use in these unit operations. So looking first at the context. So it should be no surprise to anyone that decarbonisation efforts need to proceed, and they potentially need to proceed a lot faster than they are currently. There has been a lot of talk and announcements around net zero emissions targets being set by companies, being set by countries, all in sort of support of these decarbonisation goals, and moving towards this state where we're at first net zero emissions and then ultimately negative emissions, so removing CO2 from the atmosphere. So these decarbonisation charts come from the IPCC special report on 1.5 degrees warming. So they're the charts to get us to that stretch goal of the Paris Agreement, which is to limit temperature increase to 1.5 degrees. In the blue area, we've got these decarbonisation pathways that show us achieving the goal without actually going past 1.5 degrees. In the grey shaded area on that chart, we can see us achieving the goal, but actually going past 1.5 and bringing it back. What it shows, though, is in each case, decarbonisation pretty much needs to start straight away. If we're going to go for a bit of overshoot, we've got some time, but still not much. We're still sort of decreasing at a pretty great rate of knots from sort of 2030 in those. But the later we delay, the more time we take to peak and start coming down, the more we have to rely on removing emissions from the atmosphere, on negative emissions. So peaking is vital, and we need to do that straight away. Energy efficiency has a pretty big role to play in that. We are looking at needing a 7.5% reduction year on year in emissions. Last year, 2020, which was an unusual year, I think everyone will agree. Looking at for 2020, which was untold economic and human damage, and a huge change in the way that we live and work and travel, etc. That only achieved about 7 to 8% reduction from the previous year. So, we need a way to do that each year and keep that going way off into the future, and then ultimately start removing emissions. So, mitigation efforts need to concentrate around how do we reduce emissions, then how do we remove emissions, and this is where energy efficiency has a pretty big role. The IEA also recently released their net zero pathway to achieve net zero emissions by 2050. A few headline numbers came out of that, particularly stuff around no new oil and gas developments, but industry features quite a lot in here as well in this scenario. So it's a pathway, it's a scenario, it's not a forecast, it's certainly not a view of things to come, it's a view of what's required. Industry itself has a pretty big role to play in these yellow boxes. So looking at new technologies installed in heavy industry, and they'll, in the IEA scenario, be available at scale in 2030. Everything to be high efficiency motors, best in class motors, 2035. And then basically 2040, everything's at the end of its investment cycle. So any new stuff is going to be sort of very new, very efficient equipment. So then hopefully by 2050, we've pretty much got rid of all of the emissions from heavy industry as well. This scenario tries to minimize the use of offsets, concentrates a lot on energy efficiency. So it's really about, as well, to achieve zero emissions industry, how do we generate zero carbon energy? How do we then store that energy? Do we then have, or can we have high efficiency transmission or some sort of energy carrier like hydrogen or something similar to get that renewable energy to the place it's needed? But at the same time, we're also maximizing the efficiency of end users, so we don't have to generate so much energy in the first place. So we are talking about a pretty big transformation to the energy system and to the end users to enable this zero emissions, this net zero emissions industry. And to be fair, the more we can do without having to rely on offsets and carbon credits, which are useful in their own right, but certainly may not have the capacity to absorb all of our emissions. So the more we can do to reduce that prior and minimize the use of offsets or save them for the really, really hard to decarbonize industries, then the better off we'll be overall. So looking at moving to the size of the prize. So in particular, in grinding processes, in crushing and grinding, how much energy does this process, this single process, actually use? So I recently completed a report quantifying this very thing. It was commissioned by Weir Minerals in Glasgow, and it looked at what is the energy consumption in the mining industry as a whole, and then how much of that is in comminution processes, how much of that is used to crush and grind rocks to get them to the right size for use in a mineral processing plant. So comminution is a pretty big user of energy globally, right? It's a globally significant energy consumer for what is, a single piece of equipment or one or two pieces of equipment in a comminution circuit, which does mean then it's a good target for energy efficiency. So small incremental improvements in this area mean that can have a pretty big impact overall, and you can see a good emissions reduction as a result. So the total final energy use that I calculated, and final energy is energy that's used at the point of use. So it's electrons or it's diesel in mobile equipment. total final energy use is 12 exajoules for the mining industry. About 3.5% of total global energy use goes into the mining industry, which is a pretty significant number. Of that, crushing and grinding is worth about 830 terawatt hours. So about 1% of total global energy use is used in comminution in the mining industry. When we include, cement and quarrying and things like that, other processes that also use comminution, we end up around this sort of 1.5 to almost 2% of global energy use being used to turn big rocks into little rocks. And that's actually equivalent to 221 million typical UK homes. So about 3,700 kilowatt hours per year. So it's a significant chunk of energy that's going into this process, which is why we care that it's something that we should look at. When we turn that into emissions, then, because decarbonisation is the end game. In this case, we can see that the emissions intensity of the power generation, what power we're getting into a site, what power even comes into your own facilities, has a huge impact on emissions, what's called scope 2 emissions. So if we look at the emissions impact in comminution for different energy types, just taking that 833 terawatt hours, that's if the company is self-generating. So if there's a diesel power station or a gas power station on site, which is pretty common in Australia and Canada and Africa and other mining countries, we're talking about 630 down to maybe 610 million tons of emissions to go into this process for reducing size. If we're purchasing electricity, then that depends on the grid factor. So the UK has a very low emissions intensity grid, so 115 million tons for that. China has a very high emissions intensity grid because it has a lot of coal in the mix, 780 million tons. If, of course, we had renewables, and that could be either purchased or self-generated, then we would be zero emissions for that process. So a good outcome if you can get renewables, and if we can start addressing some of the intermittency issues around the mining, around renewable energy production. So moving into the opportunities themselves. So what are the things that we have available to us? And what are the ways in which we can change the equipment or change how we're doing things to minimize energy consumption and minimize emissions? So there are these ones that I'm about to mention, they're specific to mining. So they come from the mining and mineral processing industry, but they might be able to be applied to some of the industries that you're in as well. So, potential to take some lessons learned from the mining industry and apply that to some of these other applications. So to cement or to ceramics manufacture or that sort of thing. So the first thing is around optimization. This is certainly something that can be applied to any industry, and there's a lot of work that can be done just by knowing what's going on within the grinding circuit and knowing how the circuit is operating. So we can optimize the circuit to minimize what we call overgrind. So we're actually, having the material recirculating too much and grinding down to a size that we don't necessarily need to. So we can do grinding surveys, do simulation, and ensure that the circuit is providing the optimum for the downstream, and that's what's key. The grinding area is really about providing a product that can be used in the rest of the plant. In the mining context, it's about, can we get down to the right particle size so that the valuable material is liberated from the gang material, the rest of the rock. So doing these surveys and doing simulation with dedicated simulation packages can be really, really useful to see where some of the energy waste might be coming in. And like I said, it might be in recirculated load, or it might be in the way cyclones are set, or it might be in, the pulp density in a wet process as well. This is one of the lower capex opportunities. Typically, you'll uncover a few things from this sort of optimization and simulation process. and a lot of them will have pretty reasonable payback, and many times it's just about tweaking operational settings. A higher capex option is if you've got a semi-autogenous grinder, a SAG mill, or a ball mill, there's the potential, maybe, depending on what you're processing and depending on how amenable it is, to change out that technology for something like a high pressure grinding roll, or maybe some of these stirred mills or verti mills or the high intensity grinding mills. Some of this newer technology has a lot better energy efficiency. And in the case of the HPGR, the high pressure grinding roll, you could save 40% of the energy by changing to one of those. And that really comes from when you have a ball mill, you're basically expending a lot of energy turning the mill round. They're pretty big pieces of kit and very heavy and full of steel balls as well. So the high pressure grinding rolls are just sort of two rolls that have a low gap between them, and you're moving less equipment. So you use less energy as a result for the same amount of grinding. There are some additional benefits when we look at the potential for not having grinding media in there, and also lower water use. Again, it depends on the ore or the material that's being processed, but yeah, it is something that does show promise and is used quite extensively in the cement industry already. In fact, the mining industry is picking it up from the cement industry. It is a high capex option, no lies there, but if your mill is at the end of life, then it might be something to consider, or if you're building a new facility, then these are the sorts of options that we should consider. And then finally, solutions around deep tech and using artificial intelligence or big data to optimize processes on the fly. And there's, in the mining industry, this growing trend of geometallurgy, where we take a high fidelity block model of the geology, and then we marry that up to the mining operations and then to the processing plant, so we know exactly what material is coming into the plant at any one moment. And the plant could theoretically optimize itself within sort of a window, within an envelope, an operating envelope. You could also start to extend this out and apply these sorts of AI solutions to the entire enterprise. And there's certainly a use case around optimizing the overall company objective function, which is to maximize profitability, by having plant data and good quality real-time plant data linked to external data, and then optimizing and linked to, say, shipping and transport, and optimizing the entire process to take full advantage of high prices, for example. A lot of the deep tech solutions do require increased use of sensors throughout the plant. And a general comment that sensor technology is getting a lot cheaper and cheaper to deploy, and wireless technology is getting good enough to use in places like mine sites or in processing plants, etc. So you can actually increase the data flow and then use some of these tools to actually use that data. I've been to too many operations where there's a lot of data collected but not used, and that's a pretty common state of affairs. So having these computer-based solutions now to utilize that data and get information out instead of just raw data. And the final opportunity really is around challenging the whole paradigm. How do we operate these plants? So renewable energy is a great way to reduce emissions, and it's cost effective and is the cheapest cost of power today for a new build, and it's increasingly becoming the cheapest power for existing operations as well. But intermittency is something that needs to be solved. So in an off-grid operation, then we need to overbuild the renewables, install storage. For on-grid, we'll be using corporate power purchase agreements, but then you're subject to future costs. So there's a business case to be done there. But the question really, is there an opportunity to challenge the paradigm, which is just to operate 24/7? Is there a way to operate the big energy users, the grinding operations, to maybe take advantage of peak power supply? is there a way to overbuild the grinding circuit, for example, have surge capacity built in, and then turn the grinding circuit off or move to batch operations? So these are some of the things that, you know, we should be thinking about as we, you know, move the grid to hopefully a really high renewables penetration grid. So yeah, just in conclusion, comminution is currently a significant energy user for a number of industries. It will probably remain that way for some time. It takes a lot of energy to move these machines around, but these small improvements actually can have a big contribution to overall decarbonisation. So it may pay to look towards the mining industry and see what they've done or what they're doing in terms of maximising their efficiency, and see what can be ported over to other industries. All right, thank you very much. And I think there's some questions or something has come through, so yeah.
Thank you, Mark. That was a superb overview of the challenges and some potential solutions, which is the comforting side of all of this, is that there are some potential solutions. We are obviously a little bit behind on time, so if there's just any questions for Mark at this stage. Okay, so we have a poll which is now ongoing. If you want to vote for this, comminution is inherent in raw material manufacture for many foundation industries. Should this be included within the scope of the roadmap for your company sector? I think if you could have a look at that and click on the poll function, then we can have a look whether you think this is an important thing or not. I have my opinions, but I shan't influence you. Okay, so that poll is ongoing. Neil, do you want to move to the breakout session, or?
Yeah, so what I will do is I'll give people about 30 seconds to respond to the poll, because you aren't able to do that in the breakout session. So in about 30 seconds, I'll move you all into breakout rooms automatically. I may have to manually assign the odd person, but if that is an issue, I'll do that from this way. So we will have 25 minutes of breakout sessions. There'll be a 2-minute warning, and then we'll break out into the main session again, where we can continue the presentations. We built in between a 5 to 10 minute break, depending on timings.
Thank you very much. So the breakout, the intended discussion is about the talk from Mark, the presentation of Mark on crushing, grinding, scale length reduction. But you know, we can discuss more general things as well. There'll be a scribe. We'll be taking notes, and we'll be able to use this as part of our feedback on this particular workshop when we come to post the outputs from it on. We shall restart our workshop. You've had we hope to have a slightly longer break, but unfortunately we overran a little. And if we, don't adjust the time now, then you'll overrun towards the end, which I think is a little worse. So we're going to have our next speaker, who's Professor Lenny Cole from the Management School at the University of Sheffield. I haven't given all of your titles, Lenny, so I apologise. But Director of AIREC, there's a few other things, isn't there, that I've worked with you on over the years. So Lenny is one of the UK's, if not world, experts in life cycle assessment, circular economy, and so on. She has done a substantial amount of work with me previously on ceramics and devices related to ceramics, and she's going to give a presentation on the role of techno-economic and life cycle assessments in sustainable manufacturing. So if I hand over to Lenny, and we'll be following this with a breakout session to discuss how useful in general and people could consider this to be, and why we personally at the network think this is very important.
Thanks, Ian, for the nice introduction. Should I do the share screen or? Thanks for the nice introduction, Ian. So yes, I'm going to talk briefly about the role of techno-economic and life cycle assessment towards sustainable manufacturing for the foundation industry. And in particular, I will just briefly introduce what TEA and LCA are all about, and also specifically look at the applications in two examples. So LCA, so life cycle assessment is a very important decision-making tool. Basically, it helps quantify the environmental impacts of a value chain of a product by identifying potential areas where environmental impacts can be minimized. It will also help reduce burden shifting to the other parts of the value chain. And usually when we conduct LCA study, we will need to perform 4 specific steps, and this includes goal and scope definitions. Particularly in this step, we will look at defining the system's boundaries and also the functional unit of the model. And then closely followed by building the inventory analysis and the inventory, which will include input and output data for the product, and also identifying the environmental effects of those products, which will include the classification as well as doing comparative analysis. So at this stage, we will identify the indicators that we will be interested in identifying their impact. For instance, it could be related to acidification, eutrophication, land use, and so on. And then last but not least is to interpret the results from the impact assessment. So LCA is a well-established methodology. So basically we follow ISO 1440 and ISO 1444 international standard for this. Generally speaking, there are 2 specific types of methodology for LCA. So we have the process-based LCA, which is the basic LCA, and we have the hybrid LCA, which combines process-based LCA and input-output LCA. So hybrid LCA is more powerful than process-based LCA because hybrid LCA capture direct and embodied or indirect carbon emission and environmental impact in the system rather than just the direct impact. So therefore, scope 1, scope 2, and scope 3 emissions are fully catered for in the assessment. There are various software tools that are available commercially and also in the research environment to do LCA study and to map supply chain. So my group have developed such a software tool, which is called SANET's Supply Chain Environmental Analysis Tool in partnership with Microsoft. But also there are other commercially available tools such as Gabi and CIMAPRO, and also open source LCA tools such as OpenLCA, which are widely available for use and deployment. Techno-economic analysis, is very important as well, because while we are doing LCA, we can quantify the environmental impact. But when we are carrying out techno-economic assessment, we will be able to analyze the economic performance of the system. Therefore, we can combine the consideration of economic and costing, as well as the environmental impact of a given system. Because we need to balance the techno-economic performance as well as environmental performance of any given material or product or supply chain. Therefore, I think both of these methods are equally important in any decision-making process. So in one of the papers that we have published in 2017 in Energy and Environmental Science, in the paper, we have presented a generic framework that combine LCA and TEA together. So as you can see from this slide, it captures the specific inputs in the framework for TEA, techno-economic analysis, and the specific inputs required for LCA in order to conduct the analysis. So for TEA, we will, generally speaking, cater input from purchase costs, installation costs, finance, engineering, and construction costs, which are classified as part of the CapEx calculation. And then for the OpEx calculation, we capture raw material costs, energy costs, labor costs. For the LCA, emission inventory are necessary in order to do the calculation. So we will capture data such as upstream supply chain data of a given product, logistics, conversion process, which will capture those energy intensity data in the conversion process. In both of these situations, we will need a detailed understanding of the fabrication or manufacturing processes of those materials in the supply chain. So therefore, the materials processing and fabrications is applicable for both of these methodology. They then will provide an output which will quantify the costs of a given system or the environmental impact of a given system. So for simplicity, we just show the specific module cost, for instance, in USD per kilowatt hour, or greenhouse gas emission, which is CO2 equivalent. But again, in order to quantify environmental impact, for instance, there are other types of indicators that we can select as part of this assessment, in addition to greenhouse gas emission. So the first example is triboelectric nanogenerators, tanks in short, manufacturing. So applying the generic TEA and LCA framework, we look at the techno-economic and environmental impact of tanks in this particular paper. This study is our collaboration between Ian's groups and my group, and also with the group at Georgia Tech University. So put simply, we compare the techno-economic performance and environmental sustainability performance of two different modules, which has two different material composition. So module A and module B. Module A has a higher efficiency performance, and module B has a lower energy efficiency performance. But you can see here, in terms of their manufacturing or fabrication steps, they are very similar. Broadly speaking, it includes preparation of the substrate or the mass, dielectric layer, depositioned roll-to-roll process, microstructure, patterning or surface treatment, electrode wide welding, adhesion, machining, and device assembly. So we look at the processes involved in the manufacturing of both modules in this particular study. Then we define the systems boundary in the LCA. So system boundary means, in this particular case, it's a process-based LCA. So we look at the direct impact. Therefore, identifying the energy input, the natural resources input, the raw material extraction, meaning the acrylic sheet, the PET film, lead wires, fab thin layer, copper, titanium, and gold specifically as an input, and also the fabrication process. So in this particular case, batch, weighing, cutting stage, deposition stage, microstructure, patterning stage, adhesion, machining, and sealing. And then run the LCA, which will then provide the specific result for specific environmental indicator that we have selected. So in this case, we have looked at climate change, material use, carcinogen, ozone layer radiation, and so on and so forth, as you can see from the slide. And in LCA, we can quantify the midpoint impact assessment, which are those that I mentioned just now. We can also identify and quantify the endpoint assessment, which are classified into human health, ecosystem impact, and resources impact. So this is why defining the system boundary in LCA study is very important. So we know exactly where are the impacts in a particular products or in a particular system or supply chain. In terms of TEA, defining the cost parameters is very important. So getting the data for material costs, for overhead costs, and for capital costs is very important. Now, for a new material that doesn't exist, this will include identification of this data from databases, from literature, from previous studies, and from laboratory. But for materials and products that already exist, that will need input from industry partners. So by using this data, we will then be able to compute the levelized cost for USD dollar per kilowatt hour for this particular study. One of the key purposes of doing LCA and TEA is to be able to make comparisons. So we know based on the comparison and the result, whether a particular technology or particular material or product is better than the others. So comparison of tank A and B modules in this particular case, also with other materials. So as you can see here on the left, we compare tank A and tank B materials in terms of the eco indicator summarized into resources, ecosystem quality, and human health against other material composition on the left part than the other materials. And tank A in particular has the shortest energy payback period as compared to all of the others, including tank B. For example, two, we look at the environmental impact, but in this particular case, we look at hybrid LCA between KNN and PZT manufacturing. So that is lead-based, lead zirconate titanate versus lead-free material, potassium sodium niobate, piezoelectric ceramics. For KNN and PZT manufacturing, the fabrication steps include batch weighing, ball milling, drying, calcining, ball milling, drying again, sintering, and machining. All of the temperature input and the stoichiometric quantities of each of the materials compositions are captured in this particular chart. As you can see here, the temperatures needed in order to process some of these manufacturing cycle are extremely high. For this particular study, we apply hybrid LCA instead of process-based LCA. So this is the hybrid LCA system boundary for KNN and PZT manufacturing. Again, this paper is published in Energy and Environmental Science. So looking at their hybrid LCA impact for both of these material. So as you can see on the chart, we need to quantify the thermal energy input, electrical energy input for each of the fabrication stages, the material processing, material input, which will include for PZT, lead oxide, titanium oxide, and zirconium dioxide, and others. And for the KNN composition, it includes potassium carbonate, sodium carbonate, niobium, pentoxide, and others. So with this, we then apply input-output LCA, which quantify the indirect emissions, and process LCA, therefore it is hybrid LCA, and then quantify the final result in terms of the sustainability metrics shown here. This slide summarizes some of the results from this study, and of course, the full results for both studies are available in the full papers. So in terms of thermal energy, PZT and KNN, KNN consume much more thermal energy than PZT for drying, calcination, and sintering process. And for electrical energy consumption, we can see that ball milling is the most energy intensive. But if we look at the comparison between PZT and KNN, there are not much of a big difference there. When we look at the eco indicator in terms of the summarized result for resources, human health, and ecosystem impact, KNN has a much higher environmental impact from our hybrid LCA result as compared to PZT. And in terms of the three category, resources and human health impact are the largest as compared to ecosystems impact. And if we break it down into the specific processes in the supply chain, mining definitely is one of the key contributor in this particular case for KNN, but other economic sectors, this is why hybrid LCA can identify this. Transport and telecommunication processes, utilities and chemicals are also major contributors to the high emissions in the KNN environmental impact in the hybrid LCA results as compared to PZT. So looking at this a little bit deeper, so the environmental profile between KNN and PZT can be summarized in this chart, where across these 13 different types of indicators, environmental indicators, we can see that PZT has lower environmental impact as compared to KNN. And if we look at specifically in terms of what actually caused high environmental impact in KNN, the main problem or the main source is actually niobium. So the pink sections of this chart. And this is consistent broadly across all of the 13 different indicators, ranging from climate change impact, acidification, eutrophication, to air impact. So what are the key messages? The key messages really is that generic TEA and LCA framework and methodology are useful and applicable for any material, technology, product, supply chain, and system. So regardless of any product or materials or supply chain, this is very useful in order to quantify economic and environmental sustainability impact of a product or a system. And they are measurable, so it's not qualitative or just based on opinion. This quantification is really very important, especially when we are moving ahead to understand and contribute to net zero accountability for both industry and all of the important stakeholders across our system. So I think this is going to be an important requirement as well going forward in some of the bigger contract-based study, which will require understanding of scope 1, scope 2, and scope 3 emissions in their work. Therefore, the role of TEA and LCA will become even more important in that particular situation. Thank you very much for your time and attention. So I'm very happy to take any questions.
So we have time for just a couple of questions before we move on. And there is also a poll that you can undertake. And the poll is what is more important for sustainable manufacturing? And you please do that, and we can see where your ideas are when we get the results. So questions. There's a question from Mark. What are the biggest challenges in terms of data when static and LCA, and how do you go about defining the system's boundaries? Well, that's a huge question, Mark. Can you give a brief answer, Lenny, to that? That could go on for a long time.
Yes.
Sorry, Lenny. It's always the biggest challenge, I think, is those things. So
yes, data is always one of the key challenges here. So I think, we will try our best in any LCA study to get as much data as possible and accurate and robust data as possible. So this is why we work with, established group where they have insights to the technology, to the know-how, to the processes, to the material chemistry, and so on, in order to get accurate data, and combining that with literature, databases, and also industry calibration in order to make sure that we have the sensitivity done, and in order to make sure that the accuracy of the results is maintained.
Yes, it always worries me when people go straight to a database and say, this is the data that I found, and this is what it works, and you think, well, that doesn't necessarily apply to the industry that you're talking to or the company that you're talking to. And it really worries me that we use databases too often and assume that data are correct for that particular process in that particular plant.
Yeah. We cannot rely solely on databases, but sometimes
absolutely.
Sometimes if we have missing data, we don't have access to the data from industry, for instance, then we will need to rely on other sources such as literature and databases in order to make some estimation of the potential impact.
Yeah, you also perform sensitivity analysis as well, don't you, Lenny, to make sure that your output, your data, the thing that you produce at the end of it, your assessment, is not overly dependent on a source of information that may not be super reliable. So you can I'll put that in, and you can do a sensitivity analysis. One, even though that is toxic, how does the human health impact weigh more for KNN than PZT? It's in the mining and extraction process, and how the mining and extracting companies deal with the niobium pentoxide raw material, and then the way then they deal with the byproduct of that mining and that extraction. So that's why. So I can answer that one. So, yeah. So, yeah, there's a point from there. But I think we need to move on to the breakout session. So I apologize for anybody who wants to ask any further questions. You can have a chance to discuss what Lenny has said in the breakout sessions and expand upon your personal ideas of how this could be important for your industry. So I'm back. So I think we've got the poll result here that I think the overwhelming number of people have feel that performing some kind of combined environmental and techno-economic assessment of sustainability is the way forward. We've been doing this a while in high value manufacturing products, pre-commercial compared to commercialized ones. And I think this is a very, very powerful tool. Okay, let me just look at where we are with our timing. Okay, so we're a little bit behind. So if we could start again with Sam's talk at, if I just give people 4 minutes break, 4 or 5 minutes break. We start at 12:15, so we're only 10 minutes running late, and we can have okay, guys. Sorry, I time drifted on me then. So if it's okay with everybody, we can start again. I just was doing something and suddenly it was beyond the time I said, so my apologies. Hope you had a nice break, and we are going to move to our final pre-breakout session talk, which is going to be from Professor Hussam, who's referred to as Sam Juhara from Brunel University. He runs a large group built around heat recovery systems across multiple sectors, and he's going to give us a talk on, and it's a huge group, very impressive. And he's going to give us a talk on heat pipe-based heat exchangers for challenging waste heat recovery applications. And this topic has come up time and again already inside the our breakout session, I suspect in others as well. So Sam, do you want to go?
Thank you, Ian. If I can, thank you very much.
Okay.
Thank you, Ian. Thank you very much, everyone. As I said, I'll be presenting a technology that basically we've been working with various industries over the last few years on addressing some very challenging waste heat recovery applications. Some of the photos you will see have moved from TRL4 to TRL9. Some are still at TRL8. So, I will refocus after on the ceramic industry as it is strategic industry for this network. So in my presentation, I'll talk about the technology, which is a heat pipe technology, some background information if you're not familiar with it. I'll provide some sample systems in various industries apart from the ceramics, and then I'll focus on the ceramic industry just to give you an idea about our activities in this sector from products or from R&D point of view. When we talk about the heat pipes in general, well, as the name suggests, it is heat piping from A to B without the need to force any fluid through. So the heat pipe is a hermetically sealed structure. In this case, it's a tube filled with small amount of working fluid in a preconditioned surrounded by a preconditioned surface. During operation, the pipe absorbs the heat, and this heat then used to evaporate the working fluid, and this vapor then will transfer to where the cold surface is to condense and give out the latent heat. So in this way, we are boiling, condensing, and continuing the cycle. And as you know, latent heat is a very effective way of transferring heat as of the HFG value. You can see my hand here holding a heat pipe in a kettle. One thing you will notice here is a uniform temperature from the kettle to my hand, which is a characteristic of the heat pipe, and I will talk about later. Based on the working conditions, heat pipes can be for applications all the way from molten metal applications. In this case, you can see a sodium heat pipe down, or to very, very low temperatures. We went down in the lab to -100. So it depends on the requirement for the temperature. The combination between the working fluid and the shell material will be selected. Each one of us at least will have one of these heat pipes. You can see one here inside the Dell Latitude laptop. So because of this heat pipe, we managed to bring the thickness of the laptops so thin, so we don't have to put the heatsink directly on top. So the heat pipe here is taking the heat from the CPU to where space is available to get rid of the excess heat to ensure the laptop works in a nice way. There are so many characteristics about the heat pipe that I can talk about, but I'll leave those to you to check later. Mainly, basically uniform temperature in each section and ease of cleaning, maintenance, reactivity, etc. The most significant of which is the passive operation of these heat pipes. You don't have to run a fluid through them. They will actually absorb the heat from the heat source and deliver it to the heat sink. The only limitation you have is what sort of heat transfer coefficients you have on both ends and how high they are to facilitate the transfer of the heat at the required speed. Some might say, well, why don't we just use existing technologies? Well, existing technologies, or what we call conventional heat exchangers, in some challenging scenarios, they don't actually deliver because maybe the streams or the heat source have high temperature and exhaust flows, very high mass flow rates that brings in kinetic energy issues that might destabilize the system. When you have, for example, the ceramic industry or the glass industry, you have high particulates in your flow, and these tend to settle inside the heat exchanger, clogging it in the long run. In certain scenarios, I've seen one system clogged in 1 week because basically all the particulates settled inside the system and clogged it. And also it depends on the fuel you use. If you're using fuel with sulfur in it, you end up with SO2, which transforms to SO3, and then later on combining with water, the sulfuric acid. And these can be an issue, especially if you have cold spots that will lead to corrosion issues because the acids condense inside the metal. So heat pipes actually do address many of these concerns. For example, inside the hot region, the heat pipe will operate at the uniform temperature in that section, which means there is no risk of having cold spots that will lead to condensing acids and then later to corrosion. So this is a very important characteristic of this technology. And also, because in a heat pipe heat exchanger, it is really a number of heat exchangers linked in parallel. Each heat pipe is a heat exchanger. If half of them, say, go out of operation, the rest will continue to transfer the heat, which means you don't have to stop your process. You can stop your process later on during your normal maintenance cycle and then basically fix the issue and see what caused it. So multiple redundancy is something very important, and this technology actually can provide it. And payback came up earlier. Whatever we do, whatever we design, majority of the industries will not accept anything for the ROI higher than 24 months unless there is an incentive. So most of the system you will see later today in this presentation have payback of 24 months or below. Sample systems. So here's a system, basically a gas air preheater sitting at the back of a furnace. And you can see the box here, that's a heat pipe heat exchanger sitting there, transferring the heat from an exhaust to gas to preheat it before the combustion chamber. If you take it out, you can just see it's a simple bundle of tubes staggered in a certain configuration based on the thermal design. It looks simple, and from design point of view, it's not that simple, but you can see basically the multiple redundancy that I mentioned before, because each one of these heat pipes is a heat exchanger, and all these heat pipes are linked together in parallel thermally. Here's another example in the middle of the China Sea where we produce steam, and this steam is injected to the seabed to reduce the viscosity of the crude oil. Again, in this case here, we had to design, bearing in mind very limited kilogram per square meter, and also the height limitations, etc. So there were quite a few challenges that we had to overcome. And another one on wheels that is used in a shale gas extraction and condensing steam, or at the back of a biomass burner. And these are examples that if you have any questions about, I'm happy to answer, or you can email me about them later. Another example that was funded by the Newton Fund in Brazil, where we actually used the heat pipe system here to absorb heat from burning waste. And this heat, which came from a dirty source, was then used to heat clean air. And this clean air was later used to dry tea leaves. And the project was delivered successfully a couple of years ago, but it's a good example of using this technology in this area. We're refocusing now with regards to the ceramic industry. We started activities in this sector in 2015, where we looked at the process itself. It has been covered earlier today. I'm not going to bore you with the process, but we did like an energy audit to see where are the potentials for waste heat recovery in the process. And we identified a few that we can deliver solutions for. And we worked collectively with various industries in the UK, manufacturers, heat exchanger manufacturer, and with lab scale kiln providers, in this case, ITC in Spain, where we, for the first time, we managed to install a lab scale that we managed to basically used to validate our models. And that lab scale was later then utilized. You can see it here. And this system was then later utilized in a follow-on project called the DREAM project, where we actually worked with the kiln manufacturer and the company, in this case, it was Mirage, owned by Atlas Concord, where we actually installed a system in the cooling section. And this system, you can see the PNID for the system here. And this is the photo of the installed system, which was successfully installed in 2017. And it managed to recover the heat from the exhaust flow. And this heat was directly injected into the dryer, leading ultimately to reduction in fuel consumption. And you can see the data here, basically. The system was designed to deliver 100 kilowatts. And you can see during the commissioning stage, it did actually deliver that. And when you look at the design and the validation, we were extremely close. And you can see here, basically, our theory was around 100, and then we managed to get somewhere around 99 point something. And the reason for that is we used, because it's an R&D and then full implementation, we had the luxury of doing ultra sensitive modeling activities that were later proven to be correct with the validation. And these were then used for other designs after simplifying the sizing tools. So this is the validation test, and you can see the data confirming our model. And we used here the CFD for two reasons. One, to refine the thermal design to ensure we get the value that we promised. And also, because there are particles in this flow, we use the CFD to ensure that these particles will stay suspended in the flow and they will just pass the heat exchanger without staying in it. And it was proven to be successful. So the CFD here was quite helpful to help the thermal design. So from the mechanical point of view, we kept all the particles suspended, so they went to the filter after. And these are other photos from this model. And as I said, the payback is crucial. In this scenario here, you can see basically we delivered on the payback. The DREAM project was completed, but the success was really pronounced. We thought, okay, in the DREAM project, we have two technologies, CHPs and heat pipes. When we saw the success we had, we then created a consortium together, which basically focused only on this heat pipe technology and the installation of viable systems in three sectors: the ceramic sector, the steel sector, and the aluminum sector. So I'll talk here about this project called Etekina, talk only about the ceramic sector, where you can see now Etekina started a few years back. We are now in the final year in the implementation, and you can see some of these systems being manufactured. And in the Etekina project, we're looking at the firing stage. And here we take the heat from the exhaust, and this exhaust is then basically as a heat source, goes to the heat pipe heat exchanger, which then recover the heat and then provide the heat to water flow at high pressure, and this water flow then used in the process, reducing the energy demand. You can see the actual system being delivered to Italy, very heavy unit, extremely large, and it conforms to PAD4 because the water side is pressurized. The water comes out of the system at 160 degrees. And it was a huge challenge from various point of views. Also, we have the particles to worry about, and also we need to ensure that the system stays invisible to the process, so it doesn't cause any issues with maintenance or with running the process, etc. So this is the photo. The photo here is about 10 days old. With the travel restrictions, the plan was to go there next week. Unfortunately, now, if we go from the UK to Italy, we have to self-isolate in Italy. So we have to delay the commissioning. But you can see now we are nearly there with this project. So that's the Etekina project on the ceramic side. And Brunel is a technical lead of these projects anyway. So we have really the luxury of working with amazing partners on developing various technologies. You can see here the system in place now, just awaiting the actual commissioning. Again, we go on the success of these projects. So we combine success from DREAM, focusing on the heat pipe from that firing stage, Etekina on the heat pipe technology only in various issues. But then we realized while working in the projects that heat energy is important to recycle, but there is tremendous amount of water also being wasted. In exhaust in general, you do have, especially in the ceramic industry, you have water heavy or water rich exhausts, and this water is just being expelled to the ambient. So we put together a consortium and we created the IWA project. And the IWA project basically started 1st of December last year. And its focus is to recycle the heat and recycle the water. And the water that we are recycling is water in the plant itself and condensing the water from the exhaust using a heat pipe technology. made from specific materials that will withstand corrosion. And this water will then be filtered, and any components of value will be separated, and the water itself will be recycled in the plant. It's a large consortium, and so far we are making good progress in it. We have ceramic industry, we have chemical industry, we have food industry, we have also the steel industry here. And we are making, as I said, good progress working with a great team on this project. Basically, in the I-way, we're looking at the water recovery, as I said here, and so that's a new thing which we added to the energy recovery. But they come hand in hand, really, when it comes to waste heat recovery. And the system we created, we're calling it heat pipe condensing economizer, because we are condensing the exhaust. And you can see we identified already for the ceramic demo case, we identified the location. And it's basically, we are now doing the energy auditing for the actual kiln and the requirements and the passage of the heatsink when it's heated. I hope I was within the time limit. This is basically what I have. And thank you for listening.
Thank you very much, Sam. That was excellent. It gives a really good overview of the potential that there is for heat recovery. So there's a polling question again to do with low grade, high grade, or both heat recovery. What is your priority from the point of view of academic research and, of course, within your company or sector? So please, if you could have a look at that, and we'll publish the results of that, and you'll see them in real time too. So does anyone have any questions for Sam at the moment? So I have a question, Sam. So what if I was a company and I came to you with a need, what would be the lead time to get something like one of your systems up and running from concept to finish, where you're actually saving energy?
If it is a system, if you're after a system that we have already done the research and done the work on, and we have basically confirmed a viable concept for, then between design to implementation, we're looking at 3 months.
Wow, I was expecting a longer time period. That's fascinating.
Longer time would be for a new. If we have like a new area, new location, new challenges, then we have to take it through the process. But if we have already done the work in this area, we understand the constraints, we understand the challenges, then from design, otherwise it won't be industrially viable, Ian. So we design this, we design the system, we push it to TRL 8 or 9, and then our manufacturing partners will take over. And what we do then, we just design it for them, and then they do manufacturing. So 3 months is actually a good timeline.
Steve Freeman from the paper sector, your hand's raised. Do you want to ask a question for Sam?
Yeah, thanks. My question is, what sort of input temperatures are you looking the technology to work on, and what does it raise it by, and what the potential use is? Because particularly on CHP enabled sites, kind of relatively low increase in temperature isn't that much use, because you've got a lot of that sort of heat anyway. So kind of twofold question. Thanks.
I mean, the answer, Steve, is really simple. Low grade is very, very, how can I say it without, low grade heat is available in large quantities. Sometimes the question is, okay, if I recover it, what do I do with it? So this heat exchanger is capable of transferring heat from any heat source to a heat sink, as long as the heat sink fluid is at lower temperature, in simple terms. The two key elements that we need to look at from design point of view are, I mean, for example, I recover heat in a cryogenic industry, and we have basically applications in freezing, etc. So if the delta T is there, the system will work. The key thing for us is the ROI. We need to ensure the ROI is less than 2 years. And CHPs, it all depends on the exhaust outlet temperature. From my experience, anything above 100 is of use. And in one scenario, we looked at exporting heat, a district heating system, using exhaust flow that was available at 130 degrees out of the CHP unit after the heat exchanger.
Okay, I hope that answers your question, Steve. I think we should now move to the breakout session associated with Sam's talk, and same procedures, scribe, breakout session, chit chat, and we'll collate the information. Welcome back, everybody. That was a slightly shorter session just to keep us back on time for the breakout. The poll results are in. There seems to be the idea that we really need to chase heat recovery for both low and high grade heat. I think that's reasonable. High grade heat is polled slightly lower than the low grade heat, which suggests that that's perhaps there are heat recovery systems that make use of that high grade heat already, and the low grade stuff is what needs to be researched more. And I think Mark, you suggested the hub would be chasing that kind of technology. Right, so I think we're at the end. I hope everybody has found this extremely useful. The breakout sessions that I was chair of were very, very fruitful. We're progressively dealing now with quite granular issues for the foundation industries. We had road mapping and we had a launch event previously, and now we're dealing with some pretty technical stuff now. And we'll continue with that theme periodically as we move through the grants and put on these events. So please watch out for future events coming up. I think there'll be probably a little bit of hiatus over summer in terms of workshops, but they'll restart again in September. I believe that's the scheduled time. Watch out for that if you found it useful today. I did personally, and I'm quite excited about the next one. Copies of the presentation, Jared, we will make them available on our outlets and on our website, if that's okay. If you are interested, please, and you feel you've got something out of this, please join the network. If we know about you, then we can introduce you to, if you're an academic, to a company and vice versa. And then you can maybe get together to see if you want to do a feasibility study, or maybe even bigger, larger grant applications that you can do towards Innovate UK, if that's the direction of travel. Thank you. In the chat, we have the webpage of the TFI Network Plus. And do my colleagues, Bill, Susan, sorry, Cameron, I forgot your name for a second. Do you have any comments to make at the end here?
Nothing to add beyond really excellent session, great discussions in my breakout room. Really enjoyed it, and I think we've got some really good stuff to collect.
Yep, thanks everybody for your input. It's really useful, and we will be feeding this back to you in the community. I think that's the most important thing, and also using this to a degree to finesse the sort of the calls that we'll be producing in the future too. So there should be benefits in your inclusion and your contributions that you make.
Susan?
Yeah, just echo what my colleagues have said. Thank you very much for your time. Apologies, we will run a little bit over time. So, and we promise that once we are allowed to have in-person events, we will provide a very yummy lunch for you in cases like this one.
Yes, we would love to go face-to-face, and of course we're going to be waiting on government advice. But I think I hope you agree that we have optimized the workshop processes to a reasonable level anyway, and we're getting good discussions, and I hope you've all got something out of it. And that we'll see you again on future workshops, and perhaps as delegates on our Blue Skies, Greener Future webinar series, which is a little bit lower TRL, but it showcased some pretty advanced looking technology that might have an impact on the net zero carbon initiatives in the future. So thank you everybody, and thank you to Debbie and Neil for organizing this. Bye-bye, I guess is it. That's the last word.
Thank you all. Bye-bye.
Bye all. Thank you.